Hello calculus fans, welcome to section 11.9 where we continue working with power series. So if you recall in sections 11.2 to 11.6 we worked with infinite series consisting of real numbers with no variables. We could find the exact sum of an infinite series only in special cases, and one of these cases was when we had the geometric series. So what we're going to do today is we're going to look at some series that can be manipulated algebraically in order to fit into this the form here of a geometric series. One thing though, just to make a note of, so this series starts at n equals 1, this starts at n equals 0, but you can see it's the same series in both cases. So if you notice like this here, this 1, we started at 1, so 1 decreased to 0. So if this decreases here, then to make up for that, this one increases, right? So n minus 1 increased by 1 to n. So you can really start these anywhere you want to. Typically they'll start at 0 or 1, but I mean I could start this at 3 if I wanted to. I'm just going to have to adjust this. Okay, so just kind of be aware of that. But in either case, we get the same series, and we're familiar with this one, right? This is a geometric series. Either one, however you would start it, it's the same series. And we know that it converges to this as long as, and if you remember from section 11.2, this converges if the absolute value of r is less than 1, right? Geometric series. So what we're going to do is we're going to tweak this a little bit. We're going to start from here and add a variable so we can end up with a power series. So to start off, let's just suppose that a equals 1. So if we use this series here, we let a equal 1, so a is just 1. So what we would have is this. And if you list out a few of these, if I plug in a 0, I'm going to get a 1. Then you have plus r squared, plus r cubed, plus, and you would keep on going. And eventually you would get 1 over 1 minus r, right? Just like we have up here. Of course, as long as the absolute value of r is less than 1. So now what we're going to do, we're going to keep a as 1, but we're going to let r equal x. So a series would look like this. Okay, so then what we would have is we'd have 1 plus x squared plus x cubed plus, and this would equal 1 over 1 minus x, as long as the absolute value of x is less than 1, right? So this converges if the absolute value of x is less than 1. But the thing to notice now is this thing right here, this is a power series. This is a power series because each term is a power of x, right? X to the first, second, third. We're going to end up having a power series that's a polynomial. All right, so we just started with a geometric series and we ended up with this power series after making a couple substitutions. Okay, so what we have then is that 1 over 1 minus x is the same as 1 plus x squared plus x cubed plus dot 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 if the absolute value of x is less than 1. Right, so I'm just writing this in the other order. You can actually verify this by long division. So I'm going to add this little note here. This can be verified by long division. I'll maybe do this off to the side here. So this is 1 divided by 1 minus x, right? 1 divided by 1 minus x. So if we were going to long divide, I'd sort of bring this out front here. And we'd have something like 1 minus x, and then a 1 here. So we've got 1 divided by 1 minus x. And if we just start going, we're going to think, okay, I need to multiply this by something to turn it into this term here. So I'm just going to multiply by 1. So multiply by 1, and then I have 1 times this, which I write right here. So 1 times 1 minus x is 1 minus x. Then we subtract, so it becomes a negative and a positive, so that's gone. The x comes down. Then I would need to multiply this by x to get here. So I'm going to put an x here. And then x times 1 minus x gives me x minus x squared. And then, of course, we subtract. So you get x squared, and you can kind of see what's going to happen here. Then we have a plus x squared. Then we have x squared minus x cubed. We subtract. And we just keep on going. So you can verify it by long division if you want to. And then what we're going to do is we're going to look at approximating this. So let's consider this our function. This will be f of x, right? So let's consider that this right here is our function f of x. And we want to approximate this function by using partial sums right here. So if you remember from partial sums, we worked with partial sums in the previous sections. So this would be the sum of the first one term of this. So this would just be 1. And then this next one, this would be the sum of the first two terms of the series. So it would be 1 plus x. And then this one would be the sum of the first 3, right? So it's partial sums again, sum of the first 3 terms of the series. 1 plus x squared. And then likewise, s sub 4 would be 1 plus x squared plus x cubed. And you can see a pattern here. S sub 2 goes to x to the first power. S sub 3 goes to x to the second power. S sub 4 goes to x to the third power. So in general, if I had the nth partial sum for this series, it would be 1 plus x squared plus dot 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 plus x to the n minus 1. Right, if this is n, this will go to the n minus 1. And what we're going to do is we're going to try to approximate this function by using these partial sums. And we can see that as n increases, this partial sum would become a better approximation of f of x, which is this function. And it has to be here because if the absolute value of x is less than 1, doesn't that really mean then negative 1 is less than x, which is less than 1? So this is the interval of convergence here. So as long as we're in this interval, we should be able to make this partial sum be as close to this as we want just by adding more and more terms. Okay, we're going to take a look at that on the calculator. So I'm gonna put this in the calculator. I'm going to put this one in for y1. So I'm going to put this one in for y1 in the calculator, y sub 1. And I'll go with maybe this one for y sub 2, just to see what we're dealing with. Then what I'm going to do is just add some more terms on. But to do this, to make it look right, if you're going to use the TI 83 or 84, if you want to follow along, which you don't have to, but if you want to make it easy to see, I'm going to make the x window. I'm going to make x go from negative 2 to 2 on the calculator. And I'm going to let y go from negative 1 to 9. And then I'm just going to graph this in y1, put this in y2, and then kind of go from there and just kind of see. What we should notice is that the more terms we add, the more these partial sums will act like this function as long as we're in this interval here. So we've got the calculator here, and go to y equals, and we've got the original function, f of x is in y1, and our s sub 3, our partial sum approximation, is in y sub 2. So if you go to the window, x is set from negative 2 to 2, and y is from negative 1 to 9. So if we go to graph it, here's the original function. Then here's our s sub 3. Now s sub 3 is really 1 plus x squared, so this is really a quadratic. This is a quadratic, right, that's trying to approximate this function here. Now these agree at 0. If you plug in 0 to the original function or into any of those partial sums, you're going to get 1 when you plug in a 0. But we can make our approximation hug this original curve a little bit better if we add more terms. So if I go to y equals, and I'm just going to add some more terms. I'm going to go 1 plus x squared. Let's go plus x cubed plus x to the 4th plus, let's make it a 5th degree. Okay, we'll make it a 5th degree. And then if I hit graph, it will hug the curve even better. So see how this one, it hugs it closer as we get close to 0, and the errors are less as we get out. And we should be able to make it as close to the original curve as we want, as long as we're between -1 and 1, because that's the interval of convergence, just by adding more and more terms. Okay, and one more thing I'll just mention here. They've got the original curve, and then that the quadratic is just a parabola, right? It's a parabola. And if we had plotted this one, the 4th partial sum, this is a cubic, so that would look like the 5th root, like it's going to come down here and up. And if you want to see the same thing in the book, our author actually does the same example in the book. So if you have the 9th edition of the book, it's on page 787, and the 8th edition is page 753. But it just basically just does the same thing that we just did. What we'll spend a lot of the time in this section doing is finding power series representations for these functions like this. And these particular types of functions we look at are functions that can be somehow manipulated to fit into that form 1 over 1 minus r. So we want to take this original function, we want to rewrite it. We're going to rewrite this to match this form 1 over 1 minus r. And the reason we want to do that is because this form 1 over 1 minus r, we know about this one. So we know that if you have the series n equals 0 to infinity of r sub n, you get 1 plus r squared plus ... which will end up equaling 1 over 1 minus r. Okay, so that's what we want. We know that if we can make it look like this, then we can have a power series for it. So what we want to do is basically want this to be a 1. We want this to be a 1 minus, and then whatever's here is going to be an r. So we don't have to do much with this one. This one is kind of easy. So if we have x over 1 minus 9x squared, all we have to do is factor that x out, and we'll have 1 over 1 minus 9x squared. Now at this point we've got the 1 here, we've got a 1 here and a minus, right? So it fits this form. And then r, this just means that r equals 9x squared. Okay, so this means that we could rewrite this. This means that f of x, our function f of x, this could be written, so we'll say f of x can be written as, let's see, f of x, maybe we'll say this, f of x can be written as f of x equals x times 1 over 1 minus 9x squared. And now I'm going to use this right here. Okay, I've got this form here. So this is r. So if I expand this, right, I could expand this because this is set up this way. This is r, so I'm going to have 1 plus r squared, right? So what I would have is the x stays, but then using this 1 over 1 minus r, it's going to be this 1 plus r squared. So I'm going to get 1 plus r, right, plus r squared plus r cubed, and so on. Okay, so you could write it like this. So I could just basically just distribute this through, and I get x plus 9x cubed plus, and then this goes to be 81 x to the 5th, and you could keep going like that. Or we could do this. We can use the fact that once we have this form, we can write it in this summation form. Okay, so I could also write it this way. I could say this is equal to x times the summation from n equals 0 to infinity of r, right? I'm just using this right here. Yeah, I have this, or I could write it this way. And these are they'll give us the same thing. And then what you typically do here is you'll do use some rules of exponents here. So this x can come through here, can come across the summation, so x would come over here. So really what this would be the summation n equals 0 to infinity of x times. Now if you look at this, we can just use the rule of exponents, right? If we have a times b to the n, that's a to the n times b to the n. We could do that here. So this is 9 to the n times x squared to the n. So we have 9 to, whoops, I need blue there. So I need blue, so I can say 9 to the n times x squared to the n, which is just n equals 0 to infinity of x times 9 to the n times x to the 2n. Then we can do one more thing. Because these are being multiplied, I can put these in any order we want. So I can move the x over here. And this x is really the same as x to the 1, right? So what we could do is just say this is n equals 0 to infinity of 9 to the n x to the 2n plus 1. Right? So if we multiply these two, they have the same base, so we add the exponents. So we end up with this. Okay, so in the summation notation, when it's all condensed, you could write it like this. Now what we're going to do in an applied setting, because most of our problems are going to be applied, we'll typically list it out like this. So we would typically just expand these and distribute the x through, but it gets the same thing. So you can see, just to compare, if I have it written this way, this first term is going to be x, right? X, when I distribute, plus 9x cubed. Same thing here. When I plug in a 0, get 9 to the 0, which is 1, x to the 1. So my first term is going to be x, just like this. When this is 1, you get 9 to the 1, which is 9, x to the 2 plus 1, which is x cubed. So get 9x cubed, same thing we'll get here, right? So this is more of the expanded form, this is just the condensed form. Okay, but we need to find, they're always going to ask us to determine the interval of convergence. Now this is actually going to be easier than it was in 11.8. Okay, the reason it's easier is because in 11.8 we had to use a ratio test. And the ratio test fails to give us any information if r equals 1. But in the geometric series test, it's a little easier. So let me explain. So first let's find the interval of convergence. Okay, so interval of convergence, well, this is a geometric series, so we know it's convergent if the absolute value of r is less than 1. So we have to find out what r was. Well, r is 9x squared, right? That was our r, 9x squared. So we just have to solve this. 9x squared is less than 1. So that means the absolute value of 9 times the absolute value of x squared is less than 1. Absolute value of 9 is just 9. You really don't have to go through all of these steps. I want to list them all just in case anybody's not sure. So the absolute value of x squared is just x squared, and then I had to divide each side by 9, so I get here. And now I'm going to take the square root of this. Remember, in Calc 1, I always ask students this. I say, if I take the square root of x squared, do I get x? And some students will say, yeah, I think so. But then I'll ask them, what about if x is negative 3? And you see, well, if x is negative 3, it's not going to work. So actually, the square root of x squared is the absolute value of x. Okay, so we have something similar here. I need to solve this for x, so I take the square root of each side. and I end up with the absolute value of x is less than 1/3. Right, the square root of 1/9 is 1/3. And what this means is that x is going to be between negative 1/3 and 1/3. So this is going to be our interval of convergence. Or you could write it the other way, of course, negative 1/3, comma 1/3. Now the thing to remember here is the geometric series diverges at both endpoints, because if r equals 1, it diverges, right? Because remember, it diverges, the geometric series diverges if the absolute value of r is greater than or equal to 1, including equals to. So the nice thing about the geometric series when we do this, we don't have to test the endpoints. Okay, so we don't have to check the endpoints like we did in section 11.8. All right, so we get this interval of convergence, no need to check the endpoints, they're going to diverge, so this is our final answer, either like this or like this, however you prefer. So what it means is that the series is going to behave like our function. So this power series that we come up with, this power series right here, will behave like the original function as long as we're on this interval, but not necessarily anywhere else. And I know at first when you see this, you're like, well, that's kind of a small interval. What if we're working with it outside of this interval? And it turns out this is not going to be a huge thing. You're going to see a lot of the series that we use when we're using Taylor series and Maclaurin series, which is coming up pretty quickly in the next section. They have either intervals of convergence from negative infinity to infinity, or they have larger intervals of convergence where this is not as big of a deal as it might seem like it's going to be. Okay, so we've got another one here. Find a power series representation for f of x equals 2 over x minus 4 and determine the interval of convergence. Well, same as always, right? So I'm just going to make a little reminder here. We want the form 1 over 1 minus r, because 1 over 1 minus r equals the series from 0 to infinity of r to the n, right? So that's why we want it. We want it because of this. If we can find r, we can come up with our power series. So for this one, f of x equals 2 over x minus 4. Pretty easy way to make this be a 1, right? Just like we did before, we can factor that 2 out. Factor the 2 out and we get 1 over x minus 4. Now the other thing we want is we want our variable to be over here. So we need to reverse these. I need the constant on this side. Okay, so that's just going to be 2 times 1 over negative 4 plus x. And then we need this to be a 1. Which I could get this to be 1 if I factor out a negative 4, right? Or in other words, divide this by negative 4. So if I do that, we'll get 2, 1 on top, and I'm going to factor out this negative 4, which then would give me 1 minus x over 4. Right, so just to verify, we need to get back here negative 4 plus x. So if I distribute here, I'll get negative 4. Negative times negative is positive. The 4's cancel and you get x, so we're okay. But then we can pull this negative 4 out here, because really this is really negative 1/4, right? Negative 1/4, so I could pull that out here. That would give me 2 over negative 4, 1 over 1 minus x to the 4th. And I know you guys would never ever think of leaving this fraction like this, right? 2 over negative 4? Would you even hang out with somebody who does that? I didn't think so. We've got standards, right? So let's write that instead as negative 1/2. 1 over 1 minus x to the 4, or x, 1 minus, let me try that again, 1 minus x over 4. Okay, 1 minus x over 4. So this means we've got our r, right? This means r equals x over 4. So we've got the format that we need. So really what this is equal to negative 1/2 times the summation from 0 to infinity of r to the n. Okay, so this is our function as a power series. And they're equal as long as you go to infinity, as long as also we're on the radius of convergence, right? I'm going to tell you something the book is going to do. So when you look in the back of the book sometimes to check your answer, it may look a little different. So this is fine just like this. You can leave it just like this. But the book is going to, what our author will often do is say, well, this 4, that's really 2 squared. So then I could bring this negative, or I could bring the 1/2 out here. So I'm just going to show you what the book will do, okay? This is what the book will do, but you don't have to do this. So the book is going to say, all right, I'm going to leave the negative here, but I'm going to bring the 1/2 out here. Oh, I forgot something, didn't I? It's got to be, you guys are probably screaming at the computer. And we need an n there, right? Oh my gosh, I can't believe I did that. It is r raised to the n, so we need an n here. All right, sorry about that. We need this n. So then this, we got that rule from algebra, right? A over b to the n is a to the n, b to the n. So this is really x to the n over 4 to the n. So we'll have times x to the n over 4 to the n. But 4 to the n, we can do something with that, because 4 to the n, 4 is just 2 squared. So 4 to the n is 2 squared to the n, which is 2 to the 2n. So we could write this as n equals 0 to infinity, 1/2 x to the n, 2 to the 2n. And when we multiply fractions, we go straight across. This times this times this. And this is like 2 to the 1. So finally what we'll get, if you look in the back of the book for a problem like this, you may see something like this. You'll have like an x to the n on top, and in the bottom you'll have 2 to the 2n plus 1. Okay, it's equivalent to this. And it doesn't matter how you do it. So if you start listing out terms, we're going to get the same terms. It's the same series, but this is just how the book will do it sometimes. So just kind of be aware of that. We are fine just like this, but the book may keep on going if it can, especially if there's a power of 2 here and there's a 2 here. Okay, so either way is fine. But then they're going to want us to find the interval of convergence. So let's see what we have to do there. Interval of convergence is going to depend on our r, right? Our r is x over 4, so we're going to need that. So let's find this interval of convergence. Well, it converges when the absolute value of r is less than 1. So in our case, that means x over 4 is less than 1. And of course, for these absolute values, I could write it as the absolute value of x over the absolute value of 4. And the absolute value of 4 is really just 4, right? So this is, again, I'm putting every step in here. You definitely don't need to do that. And from here, I'd multiply each side by 4, so I would get the absolute value of x is less than 4. Then from there, we could rewrite this as x being between -4 and 4, or if you prefer interval notation, either of these solutions is okay. They both say the same thing, and that's the interval of convergence. And once again, no need to check the endpoints. They're going to diverge because the geometric series diverges if r equals 1. So once we get here, we're all set. This is the interval of convergence. Okay, then we've got one more. More than one. Okay, we got another one. Now, if you love partial fractions, remember in section 7.4 we use partial fractions to help us to integrate certain functions. If you like that section, you're going to like this problem. And this problem is like number 13 in the homework in the 9th edition, and number 11 in the homework you've used in the 8th edition. So you may have to use partial fractions. So if you remember using partial fractions, what we would do, because as you can see, looking at this, this is nowhere near 1 over 1 minus r, right? There's just no way to make that work. So what we're going to do is use partial fractions, break it up into two parts, and the two parts will be able to be manipulated to fit into that form 1 over 1 minus r. So with partial fractions, what we did, first thing we did is we had to factor that denominator, right? So if you factor that denominator, we end up with 3x minus 1 times x plus 1. Then what we did is we said, okay, we're going to write a over 3x minus 1 plus b over x plus 1. And then we figure out what a and b are. So to do that, what we were doing for the most part is we start with this equation right here. We multiply both sides of the equation by the least common denominator, which is always going to be this thing. So I multiply the left side of the equation by this. I'm just left with a numerator. And when I multiply the right side of the equation by this denominator, it would be like distributed through here. And if you remember, what we'll get is a times x plus 1 plus b times 3, okay, times 3x minus 1. And then we do, usually to solve this, we learn 3 different ways in section 7.4, but the easiest way, generally the kind of go-to way, is you pick an easy value of x to plug in for everything and then solve for one of the constants a or b. So looking at this one, if I let x be -1, this term completely goes away, so I'm going to do that. I'm going to say let's let x equal -1 and see what happens. If I plug it in here, I'm going to get -7 minus 1, which is -8. And I plug in -1 here, this goes away, it just becomes 0, and I'll get b times -1 here gives me -3 minus 1, which is -4. Okay, so then this, you can see if I divide both sides by -4, I get b equals 2. Okay, so the other one, I could plug in a 1/3 here, but then we're going to have to work with a bunch of fractions. It's okay to do that, but I'm just going to plug in x equals 0. Okay, plug in 1/3 works just fine. I don't know which one's easier. Maybe they're both about the same, but if I just plug in a 0 for x, I'm going to get -1 equals, right? Plug a 0 in there. And then I'll get a times 1, right? I plug in a 0, so I just get a. Plus b, which I'm going to write as a 2. I know b is 2. I'm just going to put a 2 there. I plug a 0 in here. I'm going to get -1. So -1 equals a minus 2. Right, a minus 2. So I add 2 to both sides. I get 1 equals a. Okay. So then what we've got is this. We've got our original expression, 7x minus 1 over 3x squared plus 2x minus 1 is exactly the same as 1 over 3x minus 1 plus 2 over x plus 1. Right? So these are the same. We found this out using partial fractions. And if you remember in 7.4, we were trying to integrate something like this, then we'd integrate these both individually using natural logs, and it was kind of an easy integral from that point. But this time, of course, what we're going to do is we want these two parts to look like 1 over 1 minus r. So we'll just individually have to manipulate each of these to fit into this format. Okay, so you should probably press pause and see if you can make that happen. See if you can make these look like this, and then check back. All right, so hopefully you're doing this on your own. So this one I'm going to go -1 plus 3x. I want the constant to go first. This other one, whoops, I'm going to have to factor out a 2, right? Factor out a 2 and go 1. And I'm just going to write it as 1 plus x. So factor the 2 out to get a 1 here. X plus 1 I just wrote is 1 plus x. Now over here I need a 1 here. So I'm going to have to maybe factor out a negative 1 out of the bottom. So this to give us 1 on top, I need to factor out a negative 1, and I'll get 1 minus 3x. And then 2, so over here, I need this to be a minus, right? It's got to be a minus r. And we can do that if I go 1 minus minus x. Okay, and then we're pretty close now. I just have to take this negative and pull it out front. So I'll get negative 1 over 1 minus 3x plus 2, 1 over 1 minus minus x. And now everything's good to go. We've got this r is 3x. This r is negative x. So we could write these then, right? So we can say, this one's going to take some paper. So this is equal to, but I can rewrite this now, right? Because this is equal to n equals 0 to infinity of r to the n. So I've got the negative sign has to stay, but now I've got r. So this is going to be n equals 0 to infinity of 3x to the n. Then we have plus 2, summation from 0 to infinity. This time r is negative x, so I have negative x to the n. Okay, and I mean, you could leave it like this. This is fine. A lot of times with this, though, because negative x to the n, we can do something with that. Negative x to the n, that's the same as negative 1 times x to the n, which is then going to be the same as negative 1 to the n times x to the n. And it's generally better to write it like this because it makes it real easy to see this is an alternating series. So a lot of times you'll write it like that. But you wouldn't have to, okay? So I probably would. Like I said, it's a little easier to see that it's an alternating series, so I'd probably write this like n equals 0 to infinity, 3x to the n plus 2, n equals 0 to infinity, negative 1 to the n, x to the n. All right, but I'm just gonna tell you, when you look in the back of the book, sometimes they do some really crazy factoring. Maybe not crazy, but what they'll do, they're going to factor out the summation and they're going to factor out x to the n. Okay, so where most people would probably stop at one of these spots and they'd be just fine. Again, really when we're going to use these in applied settings, we're just going to get enough terms out of here. The next example we do will be like this. I'll show you what I mean by that. So it's not, for most of us, it's not super important to write it all in this condensed summation form, okay, because we're just going to list out a handful of terms in practice. But I'll just show you what the book is going to do. Okay, so when you look in the back of the book, you may see something like this. So what they're going to do is they're going to write this 3x to the n is 3 to the n x to the n. So they're going to put all this, they're going to basically break this up into pieces like this. So they just did one little tweak here. They just expanded this. But then what they're going to do is they will factor out the series n equals 0 to infinity of x to the n, right? And then whatever's left they'll put in here. So we're going to have, in this case, for this first series, we're going to have a negative 3 to the n. Then the second series, we're going to have a plus 2 times negative 1 to the n. Okay, so in the back of the book, you may see something like this on these kind of problems. It's really the same as what we've got. So either way, I mean, you can do this if you want to, but you don't have to. All right, so there's different ways you can write these. But then they're also going to ask us for the interval of convergence. And now in this case, we've got two series, and we need to make sure that our interval, the convergent, works for both of them. Right, so one of these series says this is r, the other one has this is r. So to find the interval of convergence, we need to consider both of these. Okay, so I'm just going to take, let's look at both of them. So as far as the interval of convergence, one of them is r equals 3x. So we have to make sure that 3x is less than 1, which means that 3 times the absolute value of x is less than 1. So the absolute value of x is less than 1/3, which means that x is between negative 1/3 and 1/3. Okay, that's one of them. The other one is negative x. R is negative x, so the absolute value of negative x has to be less than 1. And again, you don't have to go through every single step here, but I just want to make sure we understand. Negative x is just negative 1 times x, so I can split it up this way. I can put them both in their own absolute value. The absolute value of negative 1 is just 1, so that's just saying x is less than 1, which means that negative 1 is less than x, which is less than 1. Okay, so we have got two of these. We've got this one and this one. But we need the one that works for both of these, right? Because we're adding these together, so we want it to converge for both of them. You can kind of think of like a number line here. Here's 0. This one works, I'll use this color, works for all of these numbers here, right? Everything between negative 1 and 1. That works for this one, but for this one over here, I'll use a different color here. This one only works from negative 1/3 to 1/3, so that's going to be in here, right? That one works in here. We need our series to work for both of these, so we're going to need to take the one inside, this one inside. So the interval of convergence for this entire problem is going to be this one. So the interval of convergence is going to be negative 1/3 to 1/3, or if you prefer, negative 1/3 less than x, which is less than 1/3. Either of these are okay for the interval of convergence. We just have to find the one that works for both of them. Okay, so we've seen a couple examples, and now we come to the really important part, the thing that is going to make life easy for us for these power series. And it turns out it's term-by-term differentiation and term-by-term integration. Makes life really nice for us. So many properties of polynomials carry over to power series, but some do not. For example, a polynomial is defined for all values of x, right? Polynomials are so nice to use because they're defined everywhere, and they have a derivative everywhere, and we can integrate them everywhere. Whereas a power series is definable only on its interval of convergence. Yes, it's a little bit of a difference. The following theorem says that we're able to differentiate or integrate each individual term in a series just as we would with a polynomial. In other words, we can use term-by-term integration and differentiation. And it makes life really nice. So if we've got an example here of this function f of x. So we've got this function, and let's say it can be represented as a power series like this. And then what we've got is this. So here, if I plug in 0 and start going down the road here, so this is the function. When I expand this, it looks like this. Right, and here it is here. Now if I take the derivative, I can go term by term. The derivative of this constant is 0, so it's gone. The derivative of this, well, the derivative of x minus a is just 1, so I'm going to have c sub 1. When I take the derivative here, I have the power rule, so I go 2 times c sub 2 times x minus a to the 1, which is right here. And you can kind of keep going, so you can see it's just term by term differentiation. And you can even do it from here. You can do it from this summation form, because if I take the derivative here, I use a power rule, so the n comes down. So if n times c sub n times x minus a to the n minus 1, which is what we've got right here, right? And integration is similar. Now the notation is a little strange because we're trying to use a consistent notation, so it's a little different, but basically it's the same thing. Oh, one thing I should point out, This started at 0, this started at 1. It's only because the 0th term here is this one that goes away, because the constant term goes away here. So here we can just start at 1. Okay, so over here is the integral. So here's our function. Here's the integral of the function. So we get a constant term. And then you can sort of see just by using the power rule for integration, this comes up. And you can see it from here too. If we're going to integrate this, this goes up by 1 power to n plus 1. Then we have to divide by n plus 1, so it's over here. Okay, so basically it's saying we can just do term by term integration and differentiation, which makes life very nice. There's a little note here though. It says the radius of convergence is the same after we differentiate or integrate. What can change, however, is the interval of convergence. So basically, this isn't going to be super important for us, but it just means that the endpoints may change convergence or divergence. But that's it. The radius of convergence stays the same. Okay, and now here is an example that'll be closer to what we're going to do. We're going to want to approximate this. Okay, so maybe we've got an expression that doesn't have a closed form solution and we want to approximate this. Well, first, let's ask our calculator how to do this. So if you remember on the calculator, we have that finite integral command. So on the TI-83 or 84, we have that finite integral command. And you get there by pressing the math button and then going down to number 9. So math 9 gets us to finite integral. And then some of the newer calculators have math print, so you just basically type it in just like this. If you don't have math print, then you just have to type in the expression. So you have like 1 divided by 1 plus x to the 6. And then you have comma x, comma 0, comma 0.5. And when you do that, you'll get the calculator uses the Cordic algorithm, and it will get this. It'll say it's approximately 0.49889329194. Okay, so it's using the Cordic algorithm. It gets an approximation. Well, we're going to use a power series to get an approximation, and we want to get it to 6 decimal places. Okay, so you want to approximate to 6 decimal places. So what we do, we just have to come up with a power series approximation of that function. So in other words, we'll do kind of like what we've done before. If f of x is 1 over 1 plus x to the 6, this one's actually pretty easy to manipulate or tweak the way we need it. We just need 1 minus x to the 6, right? And then we've got what we need, because our r is just negative x to the 6. So what that means is that we could write this expression. We could say basically f of x is equal to n equals 0 to infinity. Negative x to the 6 is our r, so we have negative x to the 6 to the nth power. And I'm going to write this a little bit differently. I'm going to do this kind of off to the side. So negative x to the 6 to the n. It's an alternating series, so I'm going to first write it like this. And then we know that we can raise each of these factors to the nth power. So it would be negative 1 to the n, x to the 6 to the n. And that's just really negative 1 to the n, x to the 6n. So this is what we end up with. N equals 0 to infinity, negative 1 to the n, x to the 6n. Okay, so this is the same as this function right here. Okay, so let's integrate this. So the original question is 0 to 0.5 dx, 1 plus x to the 6, and we know that that is the same as 0 to 0.5, n equals 0 to infinity, negative 1 to the n, x to the 6n dx. So what I'm going to do here is I'm just going to list out a handful of terms. So this is 0 to 0.5. So I'm just going to plug in a 0. Negative 1 to the 0 is just 1. So I get x to the 0, which is 1. So the first term is going to be 1. Then when n is 1, I get negative 1 to the 1, so it's going to be a minus x to the 6. So I'm going to go minus x to the 6. Then I plug in a 2. Negative 1 squared is going to be a positive, and it's a summation, so I'm always adding. So it's going to be, I'm adding a positive this time, so you go plus. Then I get x to the 12th power, because now I plug in a 2. You can see the powers are just going to be multiples of 6, because I'm going to go, n will be 0, 1, 2, 3. It's just 6 times whatever n is. Okay, so this is 0, 1, 2. I plug in a 3 here, negative 1 cubed, which will be a minus x to the 18th plus dot, dot, dot. And then this is dx. Now, if I wanted this to be exactly equal, I'm going to have to go to infinity, but we're going to get an approximation to 6 decimal places. So x to the 18th is getting, if I put a number and raise it to the 18th power, if it's a small number, it's going to be real small, right? Which it will be. It's a small number. 0.5 is small. So it's probably going to be enough. This will probably be enough terms. But we still have to integrate, right? We haven't integrated yet. We just expressed the function as a power series. So now I integrate. So the antiderivative of 1 is x. Then I just use the power rule. Right, this goes up by 1 to 7, then I divide by 7. This goes up by 1 to 13, then I divide by 13. So I get plus 1 to 13, x to the 13th. Minus 1 19th, x to the 19th, plus dot, dot, dot. Then this is evaluated from 0 to 0.5. Now we can see that plugging the 0 in isn't going to do anything. It's just going to be minus 0. So really it's just plugging the 0.5 in. So I'm going to plug 1/2 in for all of these. So when I do this, when I plug 0.5 in the first one, of course, I'm going to get 0.5. Now when I plug in 0.5 to the second term, so I'm basically just plugging 0.5. I go 0.5 raised to the 7th power divided by 7. And what you'll get is 0.0011160,714. All right, so that is for this one. And now I plug in 0.5, raise it to the 13th power. So it's 1/2 to the 13th power. It's getting pretty small. And then multiply by 1/13, or in other words, divide by 13. And when you do that, we get plus 0.000000939. Okay, so it's getting really small. And then this last one is to the 19th power. So when I plug this one in, plug 1/2 in there, raise it to the 19th power, multiply by 1/19th. Then we get minus 0.000000100. This ends up being too small to affect our answer to 6 decimal places, right? So if we just add up these first three, terms and just round to the 6th decimal place, what we will get is 0.49889 to 6 decimal places. And that's how we do it. So we get a handful of terms here. We integrate those terms. We put in the numbers, and these are going to get smaller and smaller and smaller. So eventually, it won't affect our answer. And if we wanted 12 places of accuracy, all we would have to do is add more terms, right? Maybe go a couple more here, and then integrate a couple more, plug in 1/2 to a couple more, and we can get as accurate as we want to get. Now, of course, we do have to make sure that our interval of convergence contains these numbers, 0 to 0.5. So just to check real quick, the interval of convergence, our r we have to make sure that r is less than 1, right? Our r was negative x to the 6. Okay, well, that's going to be the same as x to the 6, right? By the way, we talked about it before. We can factor out that negative 1. And that's basically the same as, I guess you wanted to show every step we could do this. Take the 6th root, and you're basically going to get this, which means x has to be between negative 1 and 1, and it is because our integral goes from 0 to 0.5, right? Our integral goes from 0 to 0.5, so we're okay there. Now, if we weren't, one thing that we won't learn in this class, but sometimes you can use what's called complex analysis, which is like calculus with complex numbers, and sometimes you can get around these limitations. But for the most part, this interval of convergence will not be a big issue for us, and we'll see when we do the next section. And speaking of the next section, here is a question for you. Here is the question: what if we can't make the function fit 1 over 1 minus r, which oftentimes we won't? Well, no problem. We look for section 11.10, which is a more general way to approach these. So the functions we're looking at were a particular type of function that could fit into this form. Generally speaking, they won't, though. So most functions won't. But we'll come up with a more general form in the next section. So to get ready for the next section, make sure you try your homework in this section, 11.9. And as always, if you run into any trouble, just let me know.